is how you should be able to evaluate and figure it out. So what we're looking at is starting with benzoic acid, and we want to react it with a Grignard. The Grignard, we're reacting it with, is this phenyl anion. So what's the most reactive thing you see?
The charge.
Cool. So our primary focus is dealing with that negative charge. To stabilize it, what do we need to find? Positive charge. Okay, and so in this reflex, or one of the potential reflexes, is that if we actually looked at the rest of the name of this particular unit, it says carbonyl additions. So in a vacuum, what should we try and go through and do? Say that again?
Are you meaning like what we do right now?
Yeah.
I guess probably the age, because it's the most positive. Like you react the negative with the age. Take it.
Okay. So let's rewind back. Chapter being called carbonyl additions. What we might consider is trying to do a carbonyl addition. So reacting a pi bond makes sense. Just calling it pi bond is too vague though, because a carbonyl is a different type of pi bond from an alkene. How is an alkene a different pi bond than a carbonyl? For the record, we have alkene-ish pi bonds. We'll call purple within the ring. And we have carbonyl pi bond. So purple versus blue. How are they different? Non-polar versus polar. Those drastically change their end results behind them. The non-polar pi bonds need something to force them to react, which is why we need strong acids to get them to react under acid additions, or we need strong electrophiles to get them to react. Carbonyls, being polar, are already polarized, and so we don't need, quote unquote need, as strong a nucleophile to force them to go through and react. Okay? And in particular, we're going to see them act as electrophiles, again, due to the polarity of that bond. Okay? We would expect those electrons to go up to the oxygen. Oxygen, being an electronegative element, wants to hold its electrons, so that reduces the nucleophilic characteristics of the oxygen. The carbon is missing an octet, so it's screaming to have electrons share with it. So one of our reflexes might be to go through and have this system happen. Okay? Our Grignard comes in, attacks the carbonyl, breaks that carbonyl pi bond, and that would generate a product. Why would we expect it to not react with the alkene? Why should our phenyl not react with the alkene? Since you sat down. Why should it not react with the alkene?
Because benzene is quite stable.
But this isn't benzene.
Oh, it's...
With a negative charge. I know, it's okay. You can be like, dude, screw off.
Steric
That's fair.
hindrance.
Right? Our red structure is acting as a source of electrons. What do our alkenes react as?
A source of electrons.
Electron, electron, we wouldn't expect that reaction to happen. Okay.
Told you.
Good job.
They're real.
No, I was curious about the venting. But yeah, they're venting. Okay, so we could get this as a potential product. Okay, we'd have the negative charge up in the oxygen, not particularly stable, so we could predict that a follow-up reaction, which typically happens with our Grignards. We might see the addition of H+ in a workup. Okay, for the Grignard reactions, for whatever reason, they show that second step. Okay, it's officially a second step. It is just the workup. We've seen systems like this before. We're like, well, where did we get that H from? We got that H from the workup of the reaction. We just didn't specify that that's what happened. Grignards almost always explicitly show that workup. Okay? And so what we might predict would be something along these lines. Okay, for this particular question within SmartWork, a couple things might pop up as potentially problematic for us. Okay, first and foremost, what we just provided was 3 boxes, not 2 boxes. And they only gave us 2 boxes to go through and complete this reaction. Okay, so there might be something else going on here. Okay. But we could at least attempt some of this, if not all of this. Okay. If we removed all of my work, what we would find is that Ivan's already gone through and attempted this and unfortunately got it wrong. Okay. Why am I going through and pushing on this? Okay. Particularly since Ivan already changed his answer, but is still asking the question. Okay. But that's fine. We can go through and look. There's another reaction that could have happened. Okay. Our negative carbon is reacting with the carbonyl carbon because the carbonyl carbon is what charge?
Positively charged.
It's positively charged. So negative carbon's insanely unstable. They want to react with a positive as quickly as possible. The carbonyl carbon is a great positive. But is there another positive? We have the hydrogen on that oxygen. That is an acidic hydrogen. In fact, we know it's acidic because the name of that functional group is
Carboxylic acid.
a carboxylic acid. It is so acidic, we actually call it an acid. Okay, so what could have happened instead, as I redraw the Grignard sloppily there, is that the Grignard could have reacted with that hydrogen. That exceeds the octet on the hydrogen, so what happens? The electrons then shuttle to our oxygen, and we'd produce a product. And now the fun, painful question, which if I'm going to be honest, I've not thought through all the way, so we'll see what happens with this. Why should I expect one of these reactions versus the other?
It depends on the acid you use, right? Whatever's storing the proton, doesn't it kind of depend on that? Did you do that or not?
It is going to depend on the proton a little bit. Okay, a little bit. Okay, one thing I do want to help to kind of clarify with a potential argument on how we could go through and decide which one to do is let's make sure that we're comparing apples to apples. We don't want to look at the acid workup part of this reaction. Officially, there's an acid workup on the second reaction also. Okay? But the acid workup is happening kind of after the fact, so let's largely ignore that. Why would I look at one of these happening more frequently than the other?
The stability of the product?
We could go through and look at the products produced. If we take a look at the top reaction, we're forming a negative oxygen in comparison to a negative carbon. Is that reaction favorable?
The negative carbon's not, no.
Which is more stable, the negative oxygen or the negative carbon? The negative oxygen. Why?
Higher electronegativity.
Higher electronegativity. Okay, so this reaction should absolutely favor the products. This arrow makes a lot of sense. We accept that. Okay, how about the bottom reaction? We're looking at a negative carbon versus negative oxygen. Does this reaction make sense to produce products?
Yeah.
Yes. Okay. The tricky part is now comparing those two different systems, kind of like ranking acids and bases. Okay, we say, oh, that makes sense. I'm okay with that as a reaction, but now I have to compare that reaction to another one. Okay? Does it make sense for me to compare the reactants to each other?
No.
Why not? They're the same, so I shift to the products. I'm looking at negative oxygen versus
Negative oxygen.
which one's favored? So there were a couple shrugs, and the shrugs were probably in the phrasing of the question. Negative oxygen versus negative oxygen. Well, there isn't a difference, Mike. Why do we care? Okay? Because they're both negative. They're both oxygen. That means there is no size difference. There is no electronegativity difference. There's no big deal, except that's not the end of our process. We then also have to shift out to look at molecular effects. And when we shift to look at molecular effects, the molecular effect shows that this structure is resonance stabilized, which means the product of our second reaction is more favored than the product of our first reaction, which means, given the choice, which of these two reactions happens the fastest?
The one with the resonance.
The one with the resonance stabilization. Which means what this question is now getting at is that what you should be drawing in your box is that bottom system, not the top system. Okay? This question can become more challenging because we could have, all right, well, let's not do that quite yet. Are we okay with what's up here? You're good? Because this was your question?
Yeah.
Okay. If you make those changes, you should be good. There might be subtle nuances with electrons or charges or things like that, so make sure you're careful with those. Make sure you're careful with your placement of hydrogen. Just showing the single hydrogen off on that benzene should be okay, but it might get complaining about that. Okay. That looks like a positive, but that's supposed to be a negative down there. So we'll clean that up a little bit. Okay. So now let's shift and make this a little bit more challenging. Okay. In this version of this more challenging, I'm going to delete the carboxylic acid and I'm going to turn that into a ketone. Okay. Which then means over here, I'm going to delete that and turn that into a ketone as well. And we could get away with it with this structure, but let's not do that. I want to bring the OH back, but I want to bring it back in a scenario that prevents resonance stabilization.
Wait, why did you draw the benzene as like benzene? Because I think in here it doesn't have double bond.
Oh, in the question itself, it was without double bonds. Ultimately, it doesn't matter. I thought it had double bonds, but yeah, we can delete those if that makes it easier. Okay, why does it not matter?
Because the acidity.
If you drew it as a benzene versus cyclohexane, that does matter. Okay, why does it not matter to our question? What we're asking about is just the reactivity.
All the chemistry is around the oxygen and hydrogen.
All the chemistry is sitting on that one carbon. Regardless of the rest of that structure, it's 100% irrelevant. As long as we copy it across, we're fine. Okay? But the chemistry is sitting on that one carbon and that one carbon only. We don't care about the rest. Okay? So the rest of that is what we've called in some other examples as hangers. Okay? They just hang on the rest of the structure. They aren't affecting anything, but switching it from benzene to cyclohexane makes people think the reaction has all of a sudden changed. It doesn't. Focus where the chemistry is. Good question. Okay. Now what would happen through our products? Okay. In our product system, we're still going to get it either attacking the carbonyl or attacking the oxygen. Yeah? How do we decide now? Which pathway is more favorable? I think I've got everything fixed.
It's bottom.
Okay, so you still say the bottom.
Because it can do resonance, but the top of it did resonance.
Where's the resonance?
The negative oxygen
Yeah? Tell me where to move it.
to the right. But
Move it to here.
yeah, but that would kick out hydrogen.
So if it kicks out hydrogen, is that resonance?
No.
No, so don't tell me it's resonance. Okay, the next part, if we move those electrons in, what are we kicking out?
Hydrogen.
Frozen.
No, it's not hydrogen. It's H negative, I'll accept. It's hydride. It's H minus. Is H minus a good leaving group? No. Okay, so the question was about resonance. You changed the question. Still 100% irrelevant. It shouldn't happen. That's a bad leaving group. It's not going to happen. Okay? So is there resonance? No. So again, I would ask, which reaction is favored, top or bottom? And for the record, this is one hell of a harder question.
It's a bit top based on induction.
No. You're still looking at roughly the same difference in electronegativity. It's carbon versus hydrogen. You're looking at the same substitution pattern effectively around those positions. This is going to boil down to the structure of the Grignard itself. Right? Grignard reagents are highly, highly unstable, okay, and are required to be solvent stabilized. Okay, so they form very large macro structures is probably a better description of them. They aren't crystal structures, but they're larger structures where the solvent has kind of inserted itself into that system to help stabilize that negative carbon.
So would that mean the bottom one is better then?
And if we're looking at a very large macro structure, we're looking at the Grignard effectively being bulky. And if it's bulky, what's it going to preference? It's going to preference acid-base chemistry as opposed to nucleophile electrophile chemistry. Right? Which is interesting because the whole flippin' chapter is about
Nucleophile electrophile chemistry.
nucleophile addition. And yet, when we look at the Grignard, its native response is to act as a base, not as a nucleophile. Right? Which is one of the big issues when we talk about Grignard reactions. They're really neat, okay? But they are wicked reactive. So reactive that if there's anything even remotely acidic in the environment, they act as bases before they act as nucleophiles. So what do you have to do? Limit the presence of anything acidic. This means no alcohols, no carboxylic acids. Okay? All of those things are acidic enough that the Grignard will preferentially react with those. Okay? And it becomes kind of the trick question for Grignard reactions is to add an alcohol and a bunch of carbonyls. Everybody reflexes to the carbonyl chemistry, but is missing out on the bigger picture that they will also act as bases. So you have to be real careful when you go through and look at a Grignard question to make sure you don't fall into that trap of, dang, I missed the acidic hydrogen. Kind of, sort of. Okay. After that, all they're doing is nucleophile addition. They attack the carbonyl. Right? We get a simple nucleophile addition. We have to neutralize the negative. Oxygen, the easiest way to do that is to add an acid in the workup, and there we are. Right? So Grignard reactions are relatively straightforward, in my opinion, okay, for that process. But again, they are wickedly unstable. They are so unstable that would we ever think that we could form a negative carbon like that? No. And if someone can disprove us, what happens? They get to attach their name to it. Right? And if you go through and look at the literature for all our chemical reactions, when you have an oxygen acting as a nucleophile or your halogens acting as a nucleophile, for the most part, they aren't named reactions. But you look at any of the reactions where you find a negative carbon, guess what? Nearly every single one of them is a named reaction. Right? Because they're not things that are particularly stable on their own. So if we've had to create a system that somehow stabilizes them long enough to come into existence, someone's going to attach their name to it. Okay? So if you're looking to get your name memorized by students in the future, find negative carbon. Okay? You didn't have to study the bejesus out of it to prove that it exists, why it exists, how it exists, all that fun stuff. Okay? But, yeah.
So then which one is the better?
So the better system in here, you still get the bottom.
Okay,
reaction.
so it is still the bottom as well.
Yeah. Right. As long as there's that remote acidic hydrogen, it's going to follow that. Right. How crazy is this? One of my experiences in grad school, okay, if you move to a chemistry grad school program, you usually take literature study classes, okay, where you get a paper, you read through the paper, and then you present that paper to the class, and there's usually a professor in the class. And I distinctly remember a student presenting what happened. They're like, oh, they use this Grignard reagent, and they used it as a base to deprotonate it. And the instructor that's been teaching chemistry for probably 30 plus years was like, no, it can't do that. That's wrong. Floored the whole flipping class. Like, oh shit, this kid's getting reamed now and is going to fail out and drop out because the instructor just called them out for this chemistry. And it's not their chemistry. Like, they're reporting on what was written in the literature. The literature said this is what happened. And so the kid is just like dying up there. And somebody in the class was like, well, professor, Grignard reagents are notorious bases. Like, that's literally what we teach them in OChem 2, the class you teach. And the professor looked at it again. He was like, oh yeah, you're totally right. Move on. Ripped. As if nothing had happened. It was amazing. So, it is easy to make those mistakes. Okay? It is really easy to make them. Okay? That's why we have to talk through things and see what's going on with this. This is one of the reasons why I push you to talk about the chemistry. Because you may not see that simple little chemistry that somebody else sees. Okay? So cool. Yes?
Once he does the reaction, can that oxygen react with the reagent, the carbonyl?
Can this oxygen, once it's been formed, now go through and react with the carbonyl? Can you wait like 3 weeks? Okay, it's not even 3 weeks. It's probably going to show up next week. I'd have to look at the lecture flow. Okay, but when we talk about carbonyl addition, so can I erase everything that's up here? Crudely. Okay, really all we're talking about within this chapter, or in officially 2 chapters, is that we have this carbon-oxygen pi bond. We can modify structure X and Y, limited at this point. Really the only modifications we're doing is it can be carbon or hydrogen, and that's it. Okay? And then we say, well, how could it possibly react? Okay? Well, in the potential chemistries behind this, our carbonyl breaks so we can generate the resonance form. With the negative charge on the oxygen and the positive charge on the carbon. Which of those two is our primary source of reactivity?
The one with the charges.
They're both charged. The carbon. The carbon missing its octet is the primary source of reactivity. So what we need to do is react it with something. What's that something we need to react it with? A negative. I'll accept that. Okay. Really, it just needs to be a source of electrons, okay, which could be a negative. Okay. It will also be identified as a nucleophile. Well, what things could be sources of electrons? Well, we have carbons as negatives, right? Grignards. Where else could we get negatives?
Oxygen.
We could get oxygens as negatives. Where else could we get negatives? Did you say something, Josie? We could get hydrogen as negative. Nitrogen is negative. Okay? What is the difference between our carbon, hydrogen, oxygen, and nitrogens as negatives?
Some of them are more stable than others.
Ooh, some of them are more reactive than others. Which ones do you think are more reactive?
Oh, definitely the negative hydrogen.
The negative hydrogen is the most reactive of this, yeah? Okay, so what we could do is swap that around. We could say H minus and then C minus. I gotta swap those around too. N minus and O minus. Why this order? Our electronegativity is our primary difference. We got size for the hydrogen contributing to that. Okay? And what we'll end up finding is that these ones are stupid reactive. Okay? Stupid reactive isn't very scientific, so we call these irreversible nucleophiles. These ones we call reversible nucleophiles. And we bring in that language, what should that suggest to you as potentially problematic?
It can go back.
Reversible potential of two products. Why do you say two products? This brings up the idea of kinetic versus thermodynamic as potential issues. Okay, what else? Reversible, goes back. What does that mean?
It'll turn back into what it
Is there
was.
did we learn anything about reactions that are reversible, that go back and forth?
Yeah, that's
Equilibrium. So we're looking at equilibrium-dependent reactions. And I don't want to write independent up there, but equilibrium-independent reactions. Okay, they're unidirectional. I can write that. Maybe. Okay. So we have two different kind of categories. How many chapters are in this unit? Technically, there's actually three, but there's really two as far as the organization structure goes. One of them talks about the direct, easy ones, the irreversible. They produce one product only. The other ones are reversible. That's where we bring in the oxygen and nitrogen. Could the oxygen theoretically act as a nucleophile? Yeah. It acts in a reversible type fashion, though, which means all sorts of other things come into play, like Le Chatelier's principle. And Le Chatelier should remind you of equilibrium. So all of those old school concepts that you forgot from 152 are going to appear again when we look at oxygen and nitrogen as nucleophiles. Okay? You could either fall back on that old content or go, oh crap, I just need to memorize the bejesus out of that chapter. That's fine. Okay? But the first chapter we look at is theoretically the simpler versions. They're irreversible, one direction, they just go one way. Okay, so we don't have to stress about them as much. Does that make sense? Okay. So I didn't officially delay till next week, but did kind of. There is a third chapter. The third chapter is looking at how we do reduction and oxidation around that carbonyl, which is its own kind of book. But that goes back to effectively our electrophile additions / nucleophile additions. Okay? We good? Cool. That's some big picture stuff. That's important. Those are things to keep in mind as you're doing all of these reactions. Oh, that's what this is happening. That's why this is happening. That's why this is happening. To be constantly asking those questions is going to become important. It's painful, I know, but that's where you're going to pick up the learning. Next question.